Now let us derive an expression for the magnetic field produced by a solenoid. A solenoid means a insulated wire, usually copper wire, wound in the form of a helix, somewhat like this. For convenience, we are considering this solenoid in the form of a cylinder. Basically, these two are same. When you closely look at solenoid, it will somewhat look like a cylinder because all the turns are close. These turns are very close to each other, so it look like a cylinder. So for our convenience also, we are taking this solenoid in the form of a cylinder. So consider such a cylinder, such a solenoid like this. Let this be the axis of the solenoid. Let the radius of the solenoid be A. Now let us consider a thin strip of this solenoid somewhere on the solenoid like this. This one is a small strip, a circular strip of, of the same radius, that is A. This strip can be anywhere on the solenoid. Let its thickness be bx. Now let us consider a point P anywhere on the axis of the solenoid. Let its angular distance, that is, let this angle that is the angle from the point P to the extreme end of the solenoid, one of the extreme end be, let's say this one be theta 2, and let this angle, the angular distance of this point P to the other end be theta 2, sorry, theta 1. Let the point P be at a distance of x unit from the thin strip. Clear? Let this point, from this point to the one of the extreme be L1, and to the other end the length be L2. Let's name this point A, B, C, D. This length is also A. Now we have the magnetic field produced by this thin strip at the point P. Magnetic field at P due to the thin circular strip. Let's call that as magnetic field produced by dB. We already derived this expression. It acts like a circular coil. We already derived an expression for the magnetic field produced by a circular coil on its axis. If you have any doubt, you can go back and check the video. I'll put the link in the description. So it will be mu 0 times the current I a square divided by 2 into x square plus a square whole raised to 3 by 2 into number of turns n. Let n dash be the number of turns of this thin strip. Let's call this as equation number 1. So this is the expression for the magnetic field produced. We already derived this expression in the last derivation. And we know the number of turns, let n be the small letter n be the number of turns per unit length. We have number of turns per unit length is equal to total number of turns divided by this thickness. So this n dash is the number of turns of this thin strip. Implies n dash is equal to number of turns is equal to number of turns per unit length into thickness n dx. If you put this the value of n dash in equation number 1, then the equation becomes dB is equal to mu 0 I a square by 2 into x square plus a square whole raised to 3 by 2 into n dx. Let's call this as equation number 2. So in order to get the total magnetic field, you have to integrate this equation. So total magnetic field B is equal to integral. I'll write the limit later, but just write this equation mu 0 I a square n dx divided by 2 into x square plus a square whole raised to 3 by 2. Now the variable of integration is dx. So the variable is the length x, and let's say p represents the origin, so that this we have to integrate it from this L1 to L2. Since L1 is on the left and L2 is on the right, you have to put minus L1 to L2. Clear? So the equation become, before that, if you consider this triangle ADP, this one is D, we have cot theta 1. Cot theta is equal to adjacent, that is adjacent is L1 divided by opposite side A, implies L1 is equal to A cot theta 1. Similarly, if you take this triangle PBC, we have cot theta 2 is equal to adjacent, that is L2 divided by opposite side. Therefore, L2 is equal to A cot theta 2. So we can write this equation as this one: total magnetic field B is equal to integral, instead of minus L1, you can write minus A cot theta 1 to plus A cot theta 2 mu 0 I a square n dx divided by 2 into x square plus a square whole raised to 3 by 2. Let me erase this. Therefore, when you look at this equation, this mu 0 I a square and etc. are constants. So you can take that out. Therefore, B is equal to, also this 2 is also constant. So mu 0 I a square n by 2 integral minus a cot theta 1 to a cot theta 2 dx by x square plus a square whole raised to 3 by 2. Now if you look at the side of the integration, it will be very difficult when we integrate it in this form. So we have to change the value of x. So for convenience, let me erase this. For convenience, let x is equal to some a tan theta. Therefore, dx by d theta, derivative of x with respect to theta, this a will be constant. A into derivative of tan theta is sec square theta. implies dx is equal to a sec square theta d theta. Let me put this equation in here. Therefore, b is equal to mu 0 I a square n by 2 integral dx is equal to a sec square theta d theta divided by x square plus, sorry, instead of x you can write a tan theta whole square plus a square whole raised to 3 by 2. Now we have to change the limit of the integral. See here, the in this equation the variable is x, that is this length. Now that variable changes to the angle, so we have to change the limits also in accordance with the according to this angle. So we have two conditions when x is equal to minus l minus L1, that is we take this point P as origin, so anything left of P is taken as negative, and x when the value of x is L2. So x is equal to, we have minus, we already know x is equal to a tan theta. A tan theta is equal to minus L1. I'm taking this equation first. Minus L1 means minus, this is L1 minus a cot theta 1. You can cancel this a and this a. So you take this to the left. So minus tan theta is equal to cot theta 1. Let me erase this. But tan of minus theta is equal to tan minus theta, that is an odd function. Cot theta, you know, cot can be written in the form of tan pi by 2 minus theta 1. Tan pi by 2 minus tan 90 minus theta 1 is equal to cot theta. Comparing these two, you will get minus theta is equal to pi by 2 minus theta 1, implies theta is equal to, multiplying whole term with minus, this will be theta 1 minus pi by 2. So when x is equal to, minus L1, we have theta equal to theta 1 minus pi by 2. So the lower limit will be theta 1 minus pi by 2. Similarly, now take this equation. When x is equal to L2, that is x equal to a tan theta. A tan theta is equal to L2 is, we know L2 is this one, a cot theta 2. So this a and a will get cancelled. Tan theta is equal to, you can write this a and a will get cancelled. Tan theta is equal to, you can write this cot as tan pi by 2 minus theta 2. Comparing these two, you will get theta is equal to pi by 2 minus theta 2. So the upper limit is pi by 2 minus theta 2. Clear? Now we can integrate this equation. Therefore, b is equal to mu 0. We can write this as n(i)a square divided by 2 integral theta 1 minus pi by 2 pi Upper limit is pi by 2 minus theta 2 a sec square theta d theta divided by, this can be written as a square tan square theta plus a square whole raised to 3 by 2. Let me take this term inside the integral and let me separately simplify it. Otherwise, it will be very lengthy. So, this can be, these terms, this can be simplified as, we can write this as a sec square theta d theta divided by, here we can take the a square as common. So, it will be tan square theta plus 1. Outside it there will be 3 by 2. So on simplifying this, you will get a sec square theta d theta divided by this 3 by 2, you can write a square, you can, this 3 by 2 you can give to these two terms. Before that, a square 3 by 2, you know tan square theta plus 1 is sec square theta. Sec square theta, you have to put the 3 by 2 again. We know a b whole raised to m is equal to a raised to m into b raised to m. Clear? So if you simplify this, you'll get a sec square theta d theta divided by this 2 and this 2 will get cancelled, so it will be a cube. This sec square and this 2 will get cancelled, so it will be sec cube theta. You can cancel this a and here it will be a square. When you cancel this sec square theta and sec cube theta, only a sec theta remains. So the final answer will be 1 by a square. This sec theta, 1 by sec theta, taking to the numerator, it will be cos theta d theta. Clear? There will be a sec theta in the denominator. If you take that to the numerator, it will be cos theta, because 1 by sec theta is cos theta. See, this one is 1 by a square sec theta d theta. So 1 by sec theta is cos theta. So if you put that in here, the equation will be b equal to mu 0 n I a square by 2 integral theta 1 minus pi by 2 to pi by 2 minus theta 2. This term we simplified that as 1 by a square cos theta d theta. On further simplifying, you'll get b is equal to mu 0 n I a square divided by 2. This a square will come out of the integral since it is a constant, a square integral theta 1 minus pi by 2 to pi by 2 minus theta 2 cos theta d theta. This a square and a square will get cancelled. Now the integral of cos theta is sin theta. Integral of cos theta d theta is sin theta. So b is equal to mu 0 n I divided by 2. Integral cos theta is sin theta. Sin theta, first you have to put the upper limit pi by 2 minus theta 2. Now the lower limit theta 1 minus pi by 2. So b is equal to mu 0 n I divided by 2. First replace this theta with the upper limit. Sin pi by 2 minus theta 2 minus the lower limit. sine theta 1 minus pi by 2. So B is equal to mu 0 ni by 2. We know sine 90 minus theta is cos theta. So cos theta 2. This minus, if you take to inside of the sine, you can write this as sine pi by 2 minus theta 1. When you take the sine to the interior of the trigonometric function sine, the function will reverse. That is, if it is a minus b, then it will be b minus a. Now, we know sine pi by 2 minus theta is cos theta. So b is equal to mu 0 ni divided by 2 cos theta 2 plus cos theta 1. Or in other words, magnetic field B is equal to mu 0 ni by 2 cos theta 1 plus cos theta 2. So this is the expression for the magnetic field produced by a solenoid. Now we have to take the special cases. Case 1. When the solenoid is of infinite length and P is at the center, somewhat like this. Or we can take the cylinder itself. When the solenoid is of infinite length and P is at the center, this theta 1 and theta 2, this angle is theta 1 and theta 2. Theta 1, theta 2. We can take theta 1 approximately equal to theta 2 approximately equal to 0. This theta 1 and theta 2 will be 0 since it is of infinite length. Clear? So case 1, when the solenoid is of infinite length and P is at the center. The point P is at the center. Then theta 1 equal to theta 2 equal to 0. If you substitute that in here, it will be mu 0 ni by 2 into cos 0 plus cos 0. But you know cos 0 equal to 1. So mu 0 ni by 2 into 1 plus 1. You can cancel this 2 and this 2. So it will be mu 0 ni. So magnetic field at the center of a long solenoid is equal to mu 0 ni. And what if the point P is at one end of the solenoid? Let's say the point P is here. Then this theta 1, if you take this P close here, it will be like, the angle will be like this. So this theta 1 increases and at P we have theta 1 is equal to 90 degree. Theta 2 is equal to 0 because the other end is at infinity. So magnetic field, case 2, magnetic field at one end of a long solenoid, we can take theta 1 equal to 90 and theta 2 equal to 0. So B will be mu 0 ni by 2 cos 90 plus cos 0. Cos 90 is 0 and cos 0 is 1. So the expression will be B equal to mu 0 Ni by 2. 2 into 0 plus 1, which is 1. So this is the expression when the magnetic expression for the magnetic field at one end of a long solenoid. Clear.